Hello ladies and gentlemen, this is Dean from Waffly Pie, and this is Linear Algebra. So, now we get to do eigenvalues of matrices. You may have heard this term before because it's very prevalent in applied linear algebra, even though it isn't integral to the subject itself. First off, for a matrix to have eigenvalues, it needs to be diagonalizable. That means it needs to be similar to a diagonal matrix, which is sort of like saying it has a diagonal matrix as a factor. You might think that many matrices have this property, but you'd actually be surprised to find that this requirement is fairly specific. For matrix A is similar to D, the tilde here means similar, and D is a diagonal matrix. The entries of D are eigenvalues of A. However, A has to be square, and there needs to exist some matrix P such that D is equal to P inverse AP. There are some ways to solve for P, but the easiest uses eigenvectors, which we will come to in the next episode. So let's look at other ways to find just your eigenvalues alone. First off, you can't just row reduce A because the row operations allow you to manipulate the entries to your heart's content with coefficients. So there has to be some other way to specifically find D. There is, but you might not like it too much. We're going to look for the roots of the characteristic polynomial determinant of xi minus a. And I'm sorry, this type font does not use the serifs on the I, so it looks like an L or a 1. But that is capital I for identity matrix, where x is the algebraic variable that we see in algebra, calculus, so on. And yes, this does mean finding the determinant of potentially large matrices. Determinant of a minus xi also works because reflecting a function about the x-axis does not change its roots. So we've seen how to find determinants, but in this case we are going to get a polynomial because we have x. The best way to see this is to do an example. So let's look at this matrix here. And we are going to have to do some cofactor expansion. So if we want to find the determinant of this, we make the minors and do a whole bunch of expansion and then simplification, and we eventually get to x squared times x minus 3, which means that the roots of this function, which we call lambda, which is the symbol for eigenvalues, are 0, 0, and 3. Since we have two zeros, we say that the eigenvalue 0 has algebraic multiplicity 2, and lambda equals 3 has algebraic multiplicity of 1, but that is inherent, and you don't need to write that. Now that we have these eigenvalues, D is defined as these eigenvalues across the diagonal. And there is a slight problem with this scenario because of the eigenspaces, and we'll look at that next time. But that is how you solve for the eigenvalues of a matrix. Transformations have eigenvalues too. They're found the same way, and they're the same as the determinant of the matrix representation under the standard basis. And to put this into the diagonal expansion, you can also write this as the matrix representation of T under a diagonal basis, which again we will look at next time. So, until then.